Okay, calculus, section 15.1, chapter 15, begins with vector fields. So vector field is a little bit different than the vectors we've seen before. Most of them have beginning points and end points. What a vector field does instead is assigns a vector to every single point in the coordinate plane, and that vector usually depends on where the point is. So if you're at, say, 2, 4, it'll be a little bit different than if you're at 0, 3, for example, most of the time. One example of a vector field could be the gradient. For example, the function x squared plus y squared plus z squared, the gradient is the x partial plus the y partial plus the z partial, 2xi plus 2yj plus 2zk. Is a vector field in space because the vector is going to change depending on what x, y, and z are. Now, a vector field is continuous at a point if and only if its component functions m, n, and p are also continuous at the point. And m, n, and p are the functions, the components that go with I, j, and k respectively. Some common physical real-world examples of vector fields are velocity fields, gravitational fields, electrical force fields. Visually, you can look at it like this. For example, a rotating wheel. The vector, because the velocity, angular velocity of the outside of the wheel, while parallel to the inside of the wheel, is stronger because it has more distance to cover. A gravitational force, the closer you are to the center of the gravitational force, the stronger the pull, so the larger the magnitude of the vector. And airflow, as you're driving through really any situation in a car, it'll streamline to your car, so the vector of the air changes depending on your car's kind of interference there. So there's 3 visual representations of vectors. Now, let's talk about a specific kind of vector field, the inverse square field. So if r of t is a vector value function, is a position vector, the vector field f is an inverse square field if f of x, y, z equals k over the magnitude of r squared times u, where k is a real number and u is r divided by the magnitude of r, or a unit vector in the direction of r. Let's just, before we do anything, sketch some vector fields. Sketch the vector field f of xy equals negative yi plus xj. Okay. So let's just look at some points. Let's take 0, 0. If I put 0, 0, the vector will be 0i plus 0j, so there is no vector. But let's look at the point, for example, 0, 2. At the point 0, 2, y is 2, x is 0. That means my vector is negative 2i plus 0j, or going to the left 2. At negative 2, 0, it's 0i minus 2j, or going down 2. Then if you look at this pattern and keep it going, notice it kind of makes like a backwards square looking direction, and the higher or the larger numbers you pick, for example, if you go up to 5, negative 5, negative 5, and 5, it just becomes larger magnitude squares along the axes. Of course, what is this going to look like not at the axes? It's a little bit different. Let's look at the point, for example, let's go negative 2, 6. At negative 2, 6, it becomes negative 6 plus 2. So 6 to the left, 1, 2, 3, 4, 5, 6, up 2. So it goes up here. Interestingly enough, even though the vector itself doesn't make the square like the others, it does end up at a square point, negative 8, 8. And if we want to look at that, instead of negative 2, 6, we could check negative 6, 2. what happens for negative 6, 2? It becomes, the travel distance should be negative 2, 6. It also goes to that corner. So it's just, and you can continue drawing this picture all the way around, but there's some interesting things that happen with vector fields, interesting shapes that are created. Now some vector fields, sketch some vectors in the field xi plus yj. So without the minus, this is a little bit more basic. All it's saying is that for x, y, you just keep going in the direction x and y already go to. So if you look at the point 1, 1, your vector coming out of 1, 1 should be 1i plus 1j, or it's going out. So basically it's going the exact same way out from 0, 0 that the point already is. So if you're up here, you're going straight up. Down, going straight down. Any weird diagonal, like 5, 1, goes another 5, 1. It's kind of like an explosion out of the center, picture-wise. And you can continue to draw. There's more pictures online if you want to see more. But it is something interesting that happens. It's like an explosion out where the closer you are to the center, it's actually less powerful, which isn't really that accurate, but it's fine. Okay, some other definitions. A conservative vector field. A vector field F is called conservative when there exists a differentiable function F such that F is the gradient of F, little f. So the big F is the gradient of little f. The function F is called a potential function for F. So the vector field F equals 2xi plus yj is conservative because if you integrate both x and y, like they can both be integrated with respect to the variable x squared plus 1/2 y squared, because the derivatives with respect to x and y both kill the other one because it's a constant. So because the gradient of f is equal to that function, it's conservative. Now, this gives an important theorem as a sufficient condition to be conservative. So we know that for this function, we need to have f of x plus f of y, the partial functions. Now, if they're both partial functions, we know this one true fact, f of xy equals f of yx, which means if they could both be derived from the same function, if this is the x partial derivative, I could bring them back together by taking the y partial derivative here and the x partial derivative here and get to the same answer. So instead of having to test functions above, you can instead take the opposite partial below and see if you can get to the same point. And if you can, that proves that it's conservative and that there's going to be some function that is a potential function for your example. So let's just look at A real quick. So f of xy equals 1 over y squared times yi minus 2xj. So if I distribute the 1 over y squared, that's 1 over yi minus 2x over y squared j. So basically, to check conservative, I need to take the y partial of my I term and the jth partial of, or in the xth partial of my j term, see if they are equal. So let's take dm dy, where m is this. The derivative of 1 over y is negative 1 over y squared. The derivative with respect to x here is just negative 2 over y squared. So these should be even if there is a potential function. However, negative 1 over y squared and negative 2 over y squared are not even, meaning this is not conservative. And we will continue more in the next video.